are there any questions from earlier homeworks that you would like to see clarified?
I think 13 on homework 5.
Do you know what that is?
Yeah.
Okay. I'm going to grab a book.
I'm not taking a picture of it, actually. I'm just kidding, I did take a picture of it.
Nice.
Okay, so 13A says visual thinking, describe the rectangular or the regular polygon whose vertices are roots of the equation z to the fifth equals 100,000.
Okay, say it again.
Describe the regular polygon whose vertices are roots of the equation z to the fifth equals 100,000. And then part B says describe the regular polygon whose vertices are roots of the equation z to the ninth equals -1.
Equals -1?
Yeah.
So I don't know how much they want you to do there in terms of actually doing the problem, but the description would be something like this, and this is what we were kind of alluding to, and I don't remember who saw it in class and who isn't, but if you write this thing in cis form, so if you think of, and I always like to, I do it visually, because I imagine where are you going to plot the point 100,000. So that's going to be 100,000, which in my scheme is right there on the real, and 0 for the imaginary. So we can see that the r of that is the distance from the pole. And so that is going to be, so we have 100,000 is going to be 100,000 cis, and then the angle there is, I'm going to say 0 degrees. Is that okay? So when we then think of z in cis form as being r cis theta, where we don't know the r and we don't know the theta, and then we plug it into this z to the fifth, then when you take this to the fifth, it's going to become r to the fifth, and then it's going to become cis 5 theta. Is that okay? And that's going to be equal to our 100,000 cis 0 degrees. Okay, so far. So then we break it up into two pieces. We set the r parts equal and the theta parts equal. So the r to the fifth is 100,000, and the 5 theta is going to be 0 degrees plus, and then we say, so we would say in radians 2 pi times k, but here in degrees we'll say 360 times k, and we know we're going to have how many roots of this fifth degree are we going to have? 5. So the k is going to be 0, 1, 2, 3, 4. Is that okay? So then the idea is we take the fifth root here, and this was carefully constructed because since you have 5 zeros, that means 10 to the fifth is 100,000. So r is going to be the 10. So here's where we're going to get kind of to the visualization part of it. And now when we do this, we're going to divide through by the 5 to solve for theta. So we're going to get theta is going to be, well, 0 divided by 5 is still 0. And then you're going to get 360 divided by 5. Well, divided by 10 would be 36. So divided by 5, I guess, would be 72k. And then the k is still going to be the 0, 1, 2, 3, 4. So the visualization now comes into play where all of these roots are going to have the same r value of 10. So they're going to lie on a circle of radius 10. And then they're going to be evenly spaced. And so they're all going to be 72 degrees apart. So the visualization is that, you're going to imagine that, here is your argon diagram where you have real, imaginary. And so you're going to start at, 72 degrees is going to be somewhere in here. Well, actually, the first one's going to be 0. So the first one's going to be 0. And then you're going to, all these are going to lie on the same circle of radius 10. And they're going to be evenly spaced 72 degrees apart as you work your way around to those 5 roots. That kind of makes sense? So then, without doing a ton of work, we can see that, I mean, the big idea here, is can you tell in cis form what -1 is what the R is? The R will actually be positive 1. So yeah, so we would go 1, so that's 10, but we'd go 1 on the imaginary. So we'd like to keep the R positive. So the R is going to be 1, and the angle to start with is going to be 90 degrees or pi over 2 to make it be pure imaginary. So they're all going to lie on a circle of radius 1 because that's what the fifth root of 1 is. And then, you're going to start with whatever 90 or pi over 2 divided by 5, and then you're going to rotate around again, or divided by 9 rather, I guess. And so 360 divided by 9 would be 40 degrees, and then they'll be evenly spaced around. So that they all will lie on the same circle, and they'll start wherever they start and then be evenly spaced after that. That's kind of the visualization, which is kind of cool, I think. Does that help?
Yeah.
Others? So I don't think there's any way I can finish what I want to do today in a period. So I'm going to do what I can. And I've been racking my brains over this. And then you can watch the online, the support materials, Khan Academy one if you need some more. Part of it is going to be tough because I don't have yet a good way to show my calculator and keep the camera rolling. When I try to do that, when I try to switch to my calculator and project it up here, it loses the video. And so I don't have a great way of doing that, which is a lot of what we want to do on here. So I'm not sure exactly how I'm going to do that. If we get to that point, I may have to try to talk our way through it on the video and then disconnect my calculator, and we can make sure we agree. And I don't know if I can even show it up on there or not. I don't have, that's a part I don't have a good answer for yet. They're supposed to be getting me some technology that will allow me to pull up the graphing calculator on my computer screen, which then I think I could do. I don't know. It's all a big mystery to me, but at this point in time, I don't think I can do that. But that's going to happen at the end of the period if I'm lucky. All right? Okay. Stop me if I start going too fast here. So we're going to talk today about, I think that's 12.3, vector and parametric equations. And so we talked last time on the 12.1 and 12.2, we were talking about this whole idea of vectors. So we're going to go from how do you show what a vector is, conceptualize it, to how can you actually write equations, vector equations, which are kind of crazy. And then we'll go and I'll try to at least show you, try to demonstrate what my interpretation of that means. And then we'll flow from that to parametric equations, which to me seem to make more sense. It's more like about particle motion thing. So anyway, so imagine, if you will, here's our xy axis. And suppose we have some line on this plane. So we are well versed with how to talk about a line in terms of just x and y coordinates and equations, but we want to think of this as vectors. So if we imagine that there is a point on this line, say at A, and another point on this line at B, then in terms of vectors, we could think of, and we'll always call the origin O. That's kind of our default there. So we'll name the origin as the letter O. And so if we imagine, here's a vector AB that is pointing in the direction of that line. If we're going to try to bring this idea of direction in. So the idea is that we pick any point that we like on there, so some random point, and I put P to the right of B, but P could lie anywhere on this line. So we line anywhere between A and B, to the left of A, anywhere on there. then we can generate P, that is, we can say that x, y, here's where it gets kind of funky. We're going to imagine that as being this vector equation. We're going to go OA, so that vector OA is going to take us to that point, and then we're going to take a multiple of vector AB to stretch us out to P. You with me there? And so the resultant of adding those together, so I'm going to say this point P that's at XY is going, no matter where P is, so this is a generic P, is going to be OA, that vector, plus some multiple I'm going to call T times the vector AB. So for the right choice, now it's a weird way of doing it because what we're really doing is, you know, a lot of times we like to think of this as a point, but we're really saying it's that vector, right? So we're going to say that that vector OP is going to be OA plus T times AB. That's a vector equation of a line. Crazy. Isn't that weird? And remember, we can go left if we choose T to be negative, and we could get to A if we chose T to be 0, and we could get some point in here if T was something less than 1. That kind of makes sense? So it's a weird, so the picture that is in my mind, and I don't know if that's a great way to think of it, is, you know, as you go along these points, you're shooting these vectors that are going to that point. So you're generating vectors that start at the origin and terminate at that point on the line. And that's what we're getting here in this vector equation. Okay, so let's see if we can do it with some numbers. So we should say that this vector AB is known as the direction vector of that line. So we have chosen AB is called the direction vector. So it's very much acting like a slope. Right, so I mean, this is very similar in concept to point-slope form of a line, right? You start with a point, and you rise, run, and go generate other points on that line. And this is very much like that, where the direction vector AB is serving as that slope. Okay, so let's see if we can do one of these with real numbers. So find a vector equation. Find a vector equation of the line through A, which has coordinates 3, 4, and B, which has coordinates 5, 5. So first we're going to do that, come up with the equation. I'm going to want to know what is our direction vector. We're going to have to figure that out along the way. And we'll start with that. Okay, so what do we need? So you did a picture? Will that help? Yeah. Okay, so let's see what we got. Here's our XY axis. And let's say that point A is at 3, 4. So there's A. B is at 5, 5. And we're trying to come up with an equation of the line through A and B. Something like that. Okay? All right. What's our direction vector? And what's his name? AB. And remember how, I'm going to use the angle brackets. I don't think our book does, but that makes it clearly a vector. And so remember, vector is going to be tip minus tail. So we're going from A to B. So the tail 5 minus the tip 3 is going to give us x component, a horizontal component of 2. And the tip 5 minus the tail 4 is going to be 1. So our direction vector AB is going to be 2, 1. You okay with that? So then we're going to say that we're going to give, I'm going to go back to parentheses. I think that's the way our book likes to do it. XY is equal to our starting point or starting vector, whichever we want to conceptualize it as. And we're going to start this at, we could really start any way we want, but we kind of visualized it and conceptualized it as starting at A. So we can say that 3, 4 plus t, this parameter t, good, times our direction vector 2, 1.
So just to be clear, you write with parentheses now, it's the same.
It's the same,
Okay.
and it doesn't matter. Our book, I think, uses parentheses. I tend to use the angle brackets because then, in my mind, it's more clearly vectors, but it doesn't really matter. You're okay either way. Okay? So now, if we think of t as time, so which is kind of a nice way to think of that parameter t. If t is time, then what we have is a particle moving on this line, and we can track its progress. You know, at time 0, it's at A. After 1 second, it's going to be at B. After 2 seconds, it's going to go over another 2, up another 1. It'll be at C. We're free to go backwards in time. So at t equals -1, we would go down 1 and left 2. And we could use any fractions and so on. Does that make sense? So this particle is moving, if we want to think of it as a particle, as moving along that line. Or we can also think of these, you know, vectors as pointing there in time as well. That's kind of a weird way of thinking it in my mind, but that would still be a valid concept. But if t is time, then in 1 second, the particle, I'm going to say the particle moves that direction vector. It moves 2 to the right and 1 up. Does that make sense? So in that case, we would say that this 2, 1, besides being its direction vector, for this particle motion idea, this would be the velocity vector. And we could think of that, and I am going to write the angle brackets to just emphasize the fact that this is a vector. Right? So now you're saying in 1 second, it shoots up here over 2, up 1. In another second, it's going to move there. So that 2, 1 is its velocity. Where is it moving? And it's going to have a direction to it, right? Because that is a vector that takes us from A to B. So that's a velocity vector. So then what would its speed be? How do you find speed? Now speed is a scalar. It's just a plain number, always greater than or equal to 0. So we can have velocities that go backwards, but we can't have speeds that go negative. So how do you find the speed? It's the absolute value of the velocity vector. And we know how to find absolute value. We've also called that magnitude. That's going to be the square root of, it's Pythagorean, of the a squared plus b squared. So it's going to be square root of 5. So that is moving, I don't know what our units are here, I'm making them up as we go along here, say feet per second. So we're going at square root of 5 feet per second would be our speed. Does that make sense? Kind of crazy? Okay, so let's do another example, kind of like that. See if we can sort of figure this out. So we'll say now the particle. So a particle moving with constant velocity. A particle moving with constant velocity is at point A, given by 5, 3, at t equals 0, and at B, which is -4, 15, if I can read my writing, when t equals 3 seconds. Okay, so let's see if we can, first of all, can we find the velocity and speed? And then, can we find a vector equation of the object? Just say find a vector equation. Okay, how do we start? I'm open to suggestions here. But we can take turns talking here, don't everybody talk at once.
We need to solve for the direction vector?
Yes. How are we going to do that? Shall we start with vector AB? I like that idea. So AB is going to be, let's see, tip minus tail. So -4 minus 5, I think is -9. You with me there? And 15 minus 3 is 12. Is that our direction vector? I mean, not exactly, because we're going to travel from here to here in 3 seconds. So that means we want to go, our direction vector should tell us how far do we go in 1 second. So that means our direction vector, I'm just going to call it V to distinguish it from AB, it's going to be -3, 4. Does that make sense? So there's the first part of the answer A. Our direction vector is going to be a -3, 4. And then our speed, that second part of that first question, our speed is going to be, again, I'm going to write it symbolically so we get used to seeing that. It's the absolute value or the magnitude of that velocity vector. And that, in this carefully constructed problem, is going to be 5, because it's square root of 9 plus 16. So that is going to be 5. And we didn't say what the units were. So we know it's seconds. We don't know what that is. I'm just going to arbitrarily make up feet as our length unit there. So we have a speed. Okay, can we do a vector equation? All right, help me out here. Good, so we're going to say xy is going to be 5, 3. We'll start this thing at A.
Are those vectors or are those?
Either way, so either way. So, and we'll clarify this next because we're going to talk about parametrics, which are always going to be just points. And so then the parentheses will represent actual ordered pair points. So 5, 3 plus t, and then we're going to use the -3, 4 as our direction vector. We okay with that? Okay. So from here, now, this vector equation, get rid of this. From that vector equation, we can get an equation in x and y. So from the vector equation that we're looking at right there, or in general, whatever our vector equation is, we can get equations for x, or if we would prefer maybe more accurately call it x of t. I'm going to just put this in big parentheses. So x, which we can refer to as x of t, and y, or we can think of that as y of t. It'll be given both ways. So now we really are thinking about points, and so we can clarify this whole ambiguity thing about, do we mean vector, do we mean point? So we can say that the x is going to be 5 minus 3t. Does that make sense? Where I got that from? Need nods of heads. And then we can get, what's it going to be for y? Y is equal to
3 plus 14?
3 plus 14, exactly. Now these are known as parametric equations. And so and t is the parameter. A lot of times probably most of the time, but not 100% of the time, we want to think of t as being time. And so now what we get is a way of generating curves. Okay, now these are clearly the position of a particle. So it's telling us the x and the y coordinate at whatever value of t. So at time 0, this particle is starting at the 0.53. And at time 1, now the particle has moved to 2,7, and so on. And so it will trace. In this case, it's going to be a line, but we can get some pretty funky looking curves now using this idea of parametrics that aren't as restrictive as what we do with just y equals a function of x. So we can create things that will double back on itself, that will go around, and not only can we figure out where is it, what's the x and y, which is the location, that value of x and y, but we can add this idea of time into it. So when is it at a particular place, or when it's at a particular place, what was its time? When did it arrive there? Which is something we can't do with just rectangular functions, y equals f of x. Okay, so let's see if we can ask some interesting questions, maybe even answer them. So let's say that a particle moves along a line in such a way that its x and y coordinates, x and y coordinates at time t are given by, and I'm going to give you some parametric equations, x equals 1 minus t, and y is equal to 1 plus 2t. So now there's no question about is this a vector or not. These are not vectors, these are just points in the plane. And so we can follow the path. Well, it's going to be moving on a line. So we can follow the path of this thing. But what we want to know, the question we're going to ask is when and where does the particle cross the path of the curve given by x squared plus y minus 1 squared equals 25. So now we have, this opens the door, this whole idea of parametrics opens the door to questions we could never have asked before. So we can see, what we're going to answer here is, this is going to be a particle moving along a path. This is going to be, now there's no t's here, so that's going to be a fixed path. What's that going to look like? A circle, right? So we're going to have this circle that's just sitting there. And then we're going to have this particle that's going to move along a straight line. And so we're going to say, well, when and where does it cross that path of that circle? So when is it going to be at that point of intersection? And then what are the x and y coordinates of that point of intersection? Now, down the road, we could even say, we could make this a parametric equation for that circle. So now you have two particles. One's moving along a line, one's moving in a circle. Now we could ask the question, do their paths cross? Which we could have done in rectangular. Or we can ask the question, do the particles actually ever collide? That is, the particle may be, we got this particle's moving here, this one's moving around the circle. Are they going to crash and hit there? Think like the planet and a meteor path or something. Or are we going to miss, and so their paths cross, but they don't actually hit each other. We couldn't do this with just rectangular, but now with parametrics, that makes that a possibility. Cool stuff. So how do we do that as a question? Well, we say, first we're going to answer the when, so we're going to plug this into the x, that thing with the t, where we know is 1 minus t, and we'll plug in the 1 plus 2t where we see the y. Okay, so that's going to become, let's see, we got a little algebra here. 1 minus t squared plus the y is 1 plus 2t minus 1 squared equals 25. Okay. How if I'm going too fast? I'm going to square out the 1 minus t. First one squared 1, twice the product minus 4t. Second one squared is plus t squared. Let's see, the 1 and the minus, oh that's nice, they kill each other off. The quantity 2t squared is 4t squared equals 25.
When is it 2t? Yeah, when the first is 1 minus twice the product t squared.
Good point. But that's going to make a difference in our answer. Thank you. Anything else look okay? Okay, so let's see, we got the 4t squared, that's a keeper. We've got 5t squared actually. And then we got the minus 2t. Subtract the 25 from the 1, I think makes it 20 minus 24. I bet that thing factors in this carefully constructed problem. Stalling, giving you time there. Ox and diamond it, or however you do that. I'm a guess and check person myself. Just 12 and 2, right? 12 and 2. I want it to be a negative. We get it? We agree? Did you even do it?
No.
No. Killing me. Why did I even ask? I knew the answer to that. So one when is going to be after 12/5 seconds, or 2.4 seconds. And the other one is going to be a -2. And we're okay with negative times a lot of times here. Okay, so far. So that's the first question, when. Now we need the where. So to get the where, we're going to have to go back to where we get the location is given with x and y coordinates. So we're going to say x is going to be, let's see, 1 minus 12/5. So it's 5/5 minus 12/5, that's a -7/5. Did I do that right? You guys are way too trusting. Thank you. Y is going to be 1 plus 2 times 12/5. So that's 1 plus 24/5. So 29/5. So that's one place is going to be -7/5 and 29/5. It's going to be a location of where they cross. That's going to be at t equals 12/5. And at t equals -2, we're going to get 1 minus -2 is going to be 3. And -4 plus 1 is -3. Getting 3 -3. Did I do that part right? Okay, well, am I about out of time? Well, I did not get nearly where I wanted, so we'll have to see. I may, so I haven't talked about how to eliminate the parameter yet, and I haven't done any graphing. We'll have to see. I may have to slow things down a little bit, but give it a try. See if you can watch the video, see if you can make sense of it, but I may come back tomorrow and spend another day on this. I just have to push everything else back. I'm not sure I can in good conscience move on.
Did he, what's the number? Oh, in a realistic sense, what does the negative time mean?
Say it again.
In a realistic sense?
So in a realistic sense is, we observe this particle starting when we arrive on the scene. But that particle is probably moving before we started observing it.
So if we're given an equation where the particle did not start moving until we got there, what's our negative time?
Then we would probably not include the Good question. Let me stop the clock, please.